learned the pigeonhole principles, the simple form, and last lecture we have read some of the applications, the different type of applications that we can solve using pigeonhole principle. Today again we will continue to solve problems using pigeonhole principle in simple form. So, we see again some simple applications that we can solve. One such applications, mainly we are discussing the numerical problems. So, see some applications. So, write the problem that again this is a number theoretic problems, that from the integers one to 200 we choose 101 integers. Now, we have to show that among the integers chosen, these 101 integers that we have chosen, there are 2 integers such that one of them is divisible by the other. So, again I repeat the statement, problem statement, that we have 200 integers 1 to 200 and we choose any 101 integers. We have to show that among these 101 integers there are always 2 integers such that one will be divisible by the other. So, we will try to solve this problem using pigeonhole principle in simple form. Now, first we see one property of elementary number theory. So, by factoring out as many 2's we can, we know that property is that any integer can be represented, we say that any integer can be written as, say if the integer is n, then this is 2 to the power k into a. That means, k number of 2's we have taken from n, from the factor of n, and a is one odd integer. So, here where k greater than equal to 0 and a is an odd integer. So, first we see that for small integers what are the values of k and a. So, if n equal to 1, then I can write that k equal to 0, a is 1, since 2 to the power 0 into 1 is 1. Similarly, if n equal to 2, I can write that k equal to 1 and a equal to 1, since 2 to the power 1 into 1 equal to 2. So, it is valid. Now, for all primes, that means when n is prime number, we get, that is when n is prime, that n equal to 2 to the power k into a, that means here k equal to 0 and a is odd. So, n is prime, I should write other than 2, because other than 2. So, a is odd number. And for all even numbers, so for other integers, even or odd, other integers, even or odd, we can write or we can represent n as 2 to the power k into a, okay, where a is odd number. For even, we must get at least 1 2, that means power of k is in that case greater than equal to 1. So, now we consider some odd integers from 135 to 199. Since my numbers given are 1 to 200. So, how many odd integers are there in 1 to 199? So, there are 100 odd integers, from 1 to 199, that a can take any value of this from 1 to 199. I can take a value. Now, say we choose two numbers, two integers, say n1 equal to 2 to the power r into a and n2 equal to 2 to the power s into a. Now, since there are 100 odd integers, now if we choose 101 integers, then there must be two integers for which the a value is same. Here we applying pigeonhole principle. Since we have 100 odd integers, that means 100 different values of a. That can be treated as a pigeonhole, and the 101 integers chosen from 1 to 200, that we can take as the pigeons. So, two integers have the same a value. And that two numbers we have taken n1 equal to 2 to the power r into a and n2 equal to 2 to the power s into a. So, if r greater than s, then n1 is divisible by n2, or if s greater than r, then n2 is divisible by n1. So, we prove that there exist. So, it is proved that there are two integers among the chosen 101 integers from 1 to 200, such that one is divisible by other. And we have applied the pigeonhole principle. This is where we have applied the pigeonhole principle to show that thing. So, this is one class of numerical problems that we can solve using pigeonhole principle. Now, we see another type of applications where that some geometrical problems where we can apply normally the pigeonhole principle to solve or to show some statements to be true. So, I take a very simple problem that prove that any 5 points chosen within an equilateral triangle of side length 1. There are 2 points whose distance apart, that means the distance between these 2 points is at most half. So, this is a geometrical problem. We have a equilateral triangle and we have to show that there are 2 points within this equilateral triangle, that the distance between these two is at most half. So, we see the solution. I draw a equilateral triangle. So, ABC is an equilateral triangle. And we have to prove that there are 2 points in between in the interior of ABC, that whose distance at most half. Okay. So, now we break up the interior of triangle ABC into 4 regions. So, I give DEF. So, these are the DEF are the midpoints of AB BC and DE. So, this AD equal to BD equal to half, and for other sides also this is true. Now, these regions I can write the 4 regions like R1 is the interior of ADE, of triangle ADE. So, this is my R1 with the points on DE, with all the points on the side DE, but excluding the point 2 points D and E, excluding the points D and E. Then I take R2 is triangle BDF. So, this is my R2 triangle BDF. Then I take triangle R3 again, this is the interior of triangle DEF, all points including the points on DF and EF, DF and EF, and excluding the point DEF, excluding DEF. I have another region R4. I take another region R4, I write here. R4 is CEF, triangle CEF. So, we get 4 congruent equilateral triangles. That means, the interior of ABC now becomes 4 regions R1, R2, R3, R4. So, if I consider any 2 points, now I can write that interior of ABC, triangle ABC, is broken up into 4 regions R1, R2, R3, R4, which are 4 congruent equilateral triangles. Now, if I consider any 5 points in the interior of triangle ABC. So, they must be in the points must be in the regions R1, R2, R3, R4. Now, if we assume that 4 among these 5 points, 4 points among these 5 points are one in each of the 4 triangles. That means that 4 points, we assume that one point is here, one point is here, one point is here and one point is here. So, the remaining points, the fifth point, now if we put, that must be in one of the triangle of these 4 triangles. So, the fifth point, when it is put or it is placed, it must be one of the in one of the regions R1, R2, R3 or R4. That means in any one of the triangle that ADE, that BDF, DEF and CEF. That means one triangle must contain 2 points. So, one triangle contains 2 points. And the distance between these 2 points is at most half. Since my BD, AD these are half and these triangles are also the equilateral triangle. So, the distance is half. So, we prove that there are always 2 points we get in the interior of equilateral triangle ABC, whose distance is at most half. Now, we consider one third application. So, this is a problem. So, I write the problem that in a room there are 10 people. None of whom aged is older than I write none of whom is older than 60. And we assume that ages are whole number, ages are whole number. So, everyone is, none of whom is older than 60, that means everyone's age is less than equal to 60, but the age each of whom is at least 1 year old. Now, we have to prove that there can be always 2 groups of these people with no common people, such that the groups of people such that the sum of whose ages are equal. So, that means I have 10 people in a room and ages are, each one is not older than 60, none of them is older than 60. So, we can always make 2 groups. So, the sum of the ages of one group is same as the sum of the ages of the other group. We have to prove this thing. So, Now, if we since 10 people are there and none of whom is older than 60, 10 people are there and none of whom is older than 60. So, I can write that the total ages cannot exceed, if I take the sum. So, total ages, that means ages of all 10 people cannot exceed 60 into 10 equal to 600. And similarly, the total ages must be greater than 10, because everyone is at least 1 year old, at least 1 year old. So, greater than 10. So, since we are taking the ages as whole number, so the ages, the sum of ages lie between the sum of ages between 11 to 600. This is greater than 100 and we are taking a whole number. So, I can consider that 11 to 600 and that will be 590. So, 5, there are 589 different sums. H sum I can tell the H sum. Now, if I consider that as if 10 people, as if the 10 numbers. So, what will be the total number of sums? The number of sums, I can write the H sums, since I am taking the sum of ages. Number of H sums that can be formed since there are 10 people, 2 to the power 10 minus 1 that can be formed with 10 people is 2 to the power 10 minus 1. This is equal to 1023. So, now I can apply the pigeonhole principle. So, this 1023 as if the number of H sums, number of sums or number of H sums I am telling, these are actually my treated as the pigeons, and the sums of ages, these 589 are the number of sums. that may have occur, number of sums that may occur. So, and these are treated as a pigeonholes. So, that means among these 1, 0, 2, 3 that we can get more than one group. So, more than one group, since 589 is less than 1023. So, more than one group among these 10 people have the h sums equal. So, we get always at least two groups whose total sum of ages are same. So, always we get two groups whose total sum of ages are same. So, see, this is a different type of problem and we can apply pigeonhole principle and we can prove that, or we can see that we can solve the problem or we can prove the statement. Now, we have read the pigeonhole principle in simple form and mainly the applications that we can solve using this simple form of pigeonhole principle. In the next lecture, we will read the strong form of pigeonhole principle.